Hello there, everybody. This is the second part of our lesson on introductory kinematics. We're not doing any acceleration or anything, just velocity, position, distance, things like that. And this is a continuation of what we had in the part 1 lesson. Just a little review of some of the concepts that we had in part 1. First, the idea of displacement. Displacement is just a change in position. It's final position minus initial position. If we're doing it one-dimensionally, that means like on a line, then we can use the letter X to represent that. Of course, what you might remember is that displacement is in fact a vector, so we could draw the little vector symbol over top of these things. Position is also a vector because it has to do with both a number, which we call magnitude, and a direction. In this case, the X direction, but it could be some other direction. And so I sometimes drop the vector symbols when it's pretty obvious what we're doing. And in this case, it would be obvious, so I would have dropped them. Let's suppose that someone travels along this rather peculiar path from this location and follows this long and winding road over to this position. By the way, the Long and Winding Road is the name of a very successful and wonderful Beatles song from their Let It Be album, and it displays the greatness of the Beatles in that they were able to produce such a great song as that and Let It Be, despite the fact that their producer was Phil Spector. They were able to overcome that. Not even the Beatles were able to overcome Yoko Ono, but that's another story. So anyway, getting back to my point, this path length is what we call the distance, and we'll mark that with a D. If we took the direct route from where we start to where we finish, that would look more like that, and we would call that a vector, and we would label it as a displacement vector, delta x. Make sense? Okay. We also had this nice formula that average velocity is displacement divided by time. That is change in position divided by time. That is final velocity minus initial velocity divided by time. Multiplying both sides by t and adding the initial position to both sides, we ended up with this thing, which we call the equation of motion. The equation of motion, again, is simply telling you the position of an object at a given time. Now, no new concepts there. Everything's the same as it was before, but we are going to do a new problem. So let's take a look. Jeff, starting 15 meters east of his house, travels at 3.2 meters per second west. Write his equation of motion, find his position after 8.24 seconds, draw his position time graph, and then have a burger with Jeff. Okay, maybe not that last part. Well, the first thing we have to do is establish our, what is it? What? That's right, frame of reference. We have to figure out what is the origin and what is a good positive direction. For this particular problem, I've selected east as the positive direction, but if you select west, that is perfectly valid. Up would be a bad choice. South would be a bad choice. The house is a good origin also because we have the first position given in reference to the house. So we'll make that the origin in this case. Now we start listing the variables that we know. His initial position is 15 meters east of his house. I write that just as positive 15 meters because east is the positive direction, so that implies east. His velocity is negative 3.2 meters per second. Notice the minus sign indicates that it's to the west. We don't have to write west. The minus sign takes care of that for us. And believe it or not, that's all we know. Now we do have one question that involves 8.24 seconds, but that doesn't have to do with the equation of motion. So we're done listing variables. So at this stage, we can start writing the equation of motion. And that might look like this. So we have position equals initial position, which is 15 meters, plus velocity, which is a constant velocity in this case, no acceleration involved. That's the negative 3.2 times time, and that's it. Now we can simplify it a little bit, and we will. And so we get for the final equation of motion that the position is 15 minus 3.2t. And that is it. We have answered the first question already. Write the equation of motion. Now the second question asks us for his position after 8.24 seconds. Here's why we do the equation of motion first. Because you see, now that we have t for the second part is 8.24 seconds, all we have to do is substitute it into the equation of motion, and that'll give us his position. Let me show you what I mean. If I write x equals 15 minus 3.2, but instead of writing t, we replace t with its value, 8.24, other than a little algebra simplification, we're done. That's pretty cool. Who would have thought something as complicated sounding as physics would be so easy? As it turns out, the calculator gives the answer of negative 11.368, but that would imply that we know the answer to the nearest thousandth of a meter. That's the nearest millimeter. Now it's silly to think we could know that when originally we only knew his position to the nearest whole meter. So we have to round this to the nearest whole meter just to be properly precise. And so the answer is negative 11 meters. Now what does that mean? Does it mean that he's at some kind of negative place? No. Well, okay, sort of. You see, if east is positive, west is the negative direction. So negative 11 meters means he's past his house and he's 11 meters west of his house. Maybe the door of his house is the actual origin. That makes sense? That's how easy physics can be if you list your variables and write your equation of motion. Okay? All right, part 3. Let's draw his position time graph. And for that, we're going to need a pair of axes. The position time graph always has time on the horizontal axis. We have to have a unit, or our unit is going to be seconds, of course. And over here, in what looks like the y-axis, that's actually the position axis. It's the, strangely enough, x-axis. And that is going to be measured in meters in this problem. Okay? And so we have a position that's x versus time that's t graph. And that's what we're developing. What we would like to do is mark off these axes in some fashion. So maybe 1, 2, 3, maybe up to 8 seconds, even up to 9 seconds. So that'll be a 9 right there. 8, 7, this will be a 6, 5, 4, this will be a 3. And our position, well, we have to be at least 15 meters, so we'll make it 5, 10, 15. Okay, so let's come down here also, negative 5, negative 10, negative 15. All right, so let's get started in graphing this equation right here. It has, if we set t equal to 0, the y-intercept is 15. So we start with a point right here. That's actually the x-intercept, isn't it? I said the y-intercept, common mistake. But here's another thing that we can do. We can also find the horizontal intercept. You see, the line that's going to pass through here, we could use the slope form, go down 3.2 and over 1 because the slope is negative 3.2. That's kind of messy. Instead, I'm just going to find where it crosses the horizontal axis. And the way we do that is we find out, when is he home? You see, that is the same question as, when is his position equal to 0? When is he at the origin? Well, if we pop that into the equation, we would write in 0 equals, because x is 0, not t, 15 minus 3.2t. Now, solving that little equation will tell us when he has a position of 0. That is, when he is back home. And if we solve that, we get that t is equal to 4.6875. I'm going to round that to 4.7 seconds. And so that means down here on the graph, after 4, there's 5, after 4.7 seconds, which is right here, he's back home. So now we have 2 points. It's going to be a straight line graph because it has constant velocity. So now we can draw our graph. Okay. Now I said it was a straight line. I don't draw them too terribly well, but that's it. That's our graph right there. And in fact, after 8.24 seconds, remember that? If we came over here to 8.24 and came down, we would find that he was 11 meters west of his house. Pretty cool, huh? So what we've learned here are a couple of things. First, a reminder. You have to set up your origin in positive direction. You have to list your variables, and that once you have an equation of motion, you can do a lot of things. You can find the position at any time, and you can find the time at any position, including when that position is 0. That would be back home. Got it? Okay, last thing to notice. Remember when I mentioned the slope of this, but we didn't use it to graph it? That the slope was negative 3.2, because that is the coefficient of the independent variable, right? That slope is also the velocity. So that is kind of a key thing to take out of this. And that is the slope of a position time graph gives us the velocity. And that is a really important concept. Anytime you see a position time graph, if you take its slope, you'll know the velocity. If the slope is negative, it has a negative velocity. If the slope is 0, that means it's not moving, which is pretty good common sense. The position's not changing. Got it? All right. Have a good day. Practice some problems. Learn that physics. Bye-bye.